Hey, um, okay. I think we should get started, right? What was your doubt? You said you posted something, right? Hello, hello, Shagun. Am I audible? Uh, Hello. Your voice is very low, actually. A lot of noise. Speak with the team. Yes, I actually talked to them. I have not heard. I have just reached out to them. They'll say that, like, I think they'll look into it. So, I mean, with you, the issue is like you have marked the questions, but you were not able to submit, and you're saying that, like, is there any way there these marked questions answers were saved, and then you take the best response, right? So like I think I have conveyed the same thing, so let's see what they like return with. Okay, then what can we do about it, right? Like the other way is like you cannot ensure that, like how do there is no way to figuring it out, right? Like what answers you have marked. Hmm. Hmm. Have you talked to them, right? Have you mailed them? No. Yeah, same actually. Uh, so let us see. Let us wait and see. Yeah. I mean, let us wait for few days. I think something. It's a long weekend. Maybe like I think Wednesday. If you don't hear back from them, I think that should be the date. Um, yeah. Well, let's see. Let's see what they say. Okay. So let us get started with today's session. You had a question regarding calculating the world coordinate projection onto the image plane, right? And you were saying that uh, the what, like, do you want to iterate, like reiterate what was your doubt? Mm-hmm. Mm-hmm. Mm, okay. Okay. Let us clear it out, right? Mm-hmm. 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 Mm. Yeah, so I mean, so actually the property is this one, right? Let me just say. right? So what they're saying is the ratio is same. The AX or yeah, so Z is this one. Yes, because your point is at the xc comma yc comma zc, right? Yes, some sort of, yes. Yeah, so everything is centered at 0. Your image plane and your world coordinates are aligned, right? So because your x, y, and z axes are aligned, right? If there was any form of rotation, this should be represented by the rotation matrix, right? But like both of them are aligned, so now what you can do is you can actually see that like this is basically the similar triangle property, right? Yeah, so the ratio is right. Okay. Okay, so like to anyone, like let me just reiterate everything to anyone who is watching it later and do not have a context of what we are talking about. So, like you have a point x comma y comma xc comma yc comma zc in the world coordinate space, right? And you have a pinhole camera which is located at 0 comma 0 at this point, right? And the ray which is coming from xc yc zc is passing through the pinhole camera and forming an image on this image plane, right? And the distance between the point where the image is formed and the center uh, is defined by focal length, which is defined as s, right? And what people generally do is, because the image is created in an inverted manner, what you can do is like just simply move the image plane into a forward toward the world coordinate, and you'll have a upright image, right? And this coordinate system is basically x, y, and z, right? And this distance should be in x, and from 0 0 to the image plane, the distance is f. So due to similar triangle property, you basically say that x by f is basically equal to xc by z, right? And you are now, if there is a question about identifying what should be the focal length, then you can simply transform this formula into x into z by xc, and you should be able to get the focal length. And similarly, if the focal length is given to you and you want to know where the image coordinate of the image in the image plane, like this is the x coordinate, so you should be able to get that as well, right? And we have seen a similar question earlier, right? So in this question there was a coordinate which was 400 comma 600 called 1200, which is this point, right, p, and is perspectively projected into the image at a coordinate uh, 24 comma 36, right? And this is in the millimeter. uh, and what was required was you want to compute the focal length, right? Camera point f, assume what is the focal length of the camera, right? So we use the similar thing where like x by f is equal to xc by z, and you should be able to get the focal length during this using this formula, right? uh, were you able to get the assignment done this time, right? The assignment was due, right? Why so? Okay. Okay. Mm, okay. I think there are few questions which we actually looked into, right? I mean, let us see. This was one of the questions, right? I think, I mean, you should be able to do it once you. I mean, just have you seen all the lectures, right? I mean, that should be the first thing, right? Mm-hmm. Yeah, I agree. I agree. So, Um, okay. So, let us see few of the questions. I think, I mean, so the motto for today is actually, I I mean, like 3D points. I think this week, I think I'll not be able to take, but I'll definitely try to motivate towards the tracking problem, right? I mean, there was one only very small part which was covered, but like it's a very big space. And I mean, if you're actually going into either industry or like moving out of machine learning, you should at least know some tools which you can use, and what are the challenges in the tracking. Those things, tracking actually is the primary objective here. And I think toward the end, I think I'll just show you some one seminal paper in the segmentation space. And I mean, in the like lectures, it was covered using like k nearest neighbors and gmms, but like the world has actually moved into the deep learning era. And so that, like, I think we should actually look into unit paper, which actually created a very good uh, like gave a very good push in the segmentation space. I think we will look into the paper. I think that is my goal for today, right? I think just few questions, then tracking, and then eventually we can actually look into the segmentation problem. Um uh, might not be very much aligned, but very will be very useful for the modern computer vision, right? So this will be beyond your traditional lectures. So I mean, I don't know, right? Like, you should whether you should expect any question from these topics, but definitely will be most useful whenever you are building something, right? Okay. Yeah. So let us look at a few other questions. So consider two identical cameras, K and K dash, whose optical axis is aligned with Z, and focal length of 0.03, right? And the with square pixels, no pinhole effect, zero skewness. What is the expression of K? What is K? K is the intrinsic matrix. And what should be your pinhole cameras should be looking at? Like, this is your space, this is your, and this is your line, which is basically uh, connecting the optical axis. So this camera has the intrinsic metric k, this has the k dash, and both are equal. And if you actually look at the formula for k, it is f of x, s is for skewness, this is tx translation, this is f of y, this is 1 0 0. You already have focal length information, right? So we have focal length 0.03, and then you simply put the focal length because there is no translation, right? Skewness is 0, right? So you should be able to get the expression of k. This was one of the questions. There was one other question which we actually looked into uh, in the last session also. So if you so let us consider a point xn, right, expressed with respect to first camera coordinate system. Suppose xn is equal to r uh, Rn plus T. T is your translation, R is your rotation matrix. So this was the rotation matrix which was given to us, and you have a translation matrix expressed, right? So what you can do is you needed to actually compute the fundamental matrix, right? Uh, so there was one more part where you need to visualize it. If you want to visualize uh, the rotation is basically 45 degrees. If you look into it carefully, this is the some sort of a cos of theta, where theta is equal to 45 degree, right? 1 by root 2, right? So your both the planes, epipolar planes, are basically rotated in 45 degrees. So if this is aligned at 0, your x is now aligned at 45 degree, right? This is the way of visualizing it. And if you want to actually, yes, definitely, right? Like, I mean, yeah. So, like, if you want to compute the fundamental metrics, I think the equation was given. If you look into the lecture, it is there. So, uh, lengthy, yeah, it is a lengthy process. But generally, I mean, if anyone is like in the real world, you will be doing it using computers. If anyone is asking you in the exam, they'll not give you 3 cross 3 matrix, or they'll give you the diagonal matrix mostly. Yeah, so yes, yes. So if you have a diagonal matrix, the inverse is basically 1 by d. Yes, because the elements will be on the diagonal only, right? And if you want to take the transpose for a yes, if the elements are different, yeah. Yeah. So the K transpose is equal to K if it's a diagonal matrix, right? Because the elements are anyway on the diagonal, right? But for inverse, what you do is like you divide by every element by 1 by d. So you can actually easily compute the K inverse transpose. I mean, there is something which you should be actually like more cautious, is uh, this TX matrix, basically cross product, right? So I mean, this is the direct formulation, but just like see, right, like what was the cross product between two vectors, right? So that I think you should actually take care of, because you actually need to give a like a more theoretical understanding, right? Ax cross b, right? The c is basically perpendicular to b and a, right? Both of them. Tx is a, if you, that is a translation vector, right? We have given the translation in which direction? T 0 comma 0 0.2 comma 0, right? This is the translation. Y space, na? Y space, right? But how do you actually represent it in a form of a matrix, right? So this, if you just go to the lecture, I mean, you should be able to see directly get it. This tx should be there, right? This tx is, x is basically for a short form of, or a cross product. So to convert it into the matrix, you write it in this form: 0 minus tz ty tz 0 minus tx minus ty tx 0. And we also only have the value for ty, right? So t has three component, right? Tx, ty, tz. Yes. So we have only translation in the y direction. So it is 0.2. So now you should just substitute your values of ty, and you should be able to get this matrix, right? You have the rotation matrix was given to you already, and K inverse is, you can actually compute using K inverse is uh, right, we have computed K now. This is the K matrix, right? You are able to get K transpose inverse. You have the T matrix, Tx matrix, you have the rotation matrix, you have the K matrix, and if you multiply everything it should turn out to be this, right? So you have the fundamental matrix with you. And what does the fundamental matrix tell you? So given a point, you have two planes, K and K dash. If any point in K dash, I should be able to map it to any point in K should be mapped to K dash using the, yes, using the fundamental matrix. That is the whole crux of the problem, right? So that leverage, this leverage basically is given by this fundamental matrix F, right? Uh, this should be fine. Uh, what is the question? Suppose you want to walk around the campus and take a picture of some picture I1 of a square circle. You are not happy, you want a larger picture, you step forward 2 meter and take a closer picture I2. If you assume that there is only a forward translation of the camera in the of the camera direction perpendicular to the image plane, the essential matrix is between the uh, I1 and I2. The essential matrix is basically gives you the rotation and the translation, right? Right. Mm-hmm. Yeah, yeah. So this is basically essential metric only. Yeah, this part, right? Right. So what it is saying is like there is no rotation, right? There is only translation. You're actually holding the camera in the similar direction. So maybe this might be the object, like, right? And you are standing somewhere here, X, Y, Z, right? Now you have taken a picture. This might be forming somewhere here, right? Now you actually translate 2 meter and then again take a picture, right? This is your optical X, Y, right? So the translation is only in one direction, that is also given to you, right? You just multiply both of them, right? So what you do is like you convert it into uh, translation matrix, which will be 0 tz ty tz0 minus tx minus ty tz0. It turns out to be this one. Just multiply both of them and you should be able to get the answer. It essentially the same, right? Because there is no rotation, it is identity matrix. Um, I think the rest were fine. I have not spent much time on actually seeing uh, the other problem. I just took a like look around and found out like they should be straightforward. Anything specific, just put it in the comment. I think we can actually take it maybe in the next session. But I mean, having said that, the essential thing here is uh, lectures. Just see through the lectures. I mean, you should be able to get like most of the questions if you go through the lectures. I mean, somewhat just extend the knowledge. These questions are just extended whatever been talked in the lectures, but that will be the case. Like if you go to any like IIT or somewhere, like you want to do MTech, Masters or PhD, like the kind of exams being taken are similar, like very similar format, and it is like the similar all over the world. So whatever has been taught is a concept and the question will be asked with the extension of that concept. So like you will not find directly same questions which has been taught. So yeah. Yeah, take it as a pinch of salt. And so next, I just wanted to show you few of the demos for tracking. I mean, I think those are actually very pretty interesting if you actually look into it. Uh, so first one, for in this, uh, you can see my screen, right? You can see there is a video type where there are multiple people. Yes, right. So this is like has been taught in this like I think this week's. Yeah, yeah. So the tracking. So there's a this these are the traditional tracking algorithms. So this is Lucas Kennedy approach where you are actually kind of optimizing on the optical flow where the object is moving and you predict, you track that object, right? So this was the tradition. So what I have done is I've created a demo for you where you can actually select object. So in tracking there is a this thing. Uh, so the traditional form of tracking was like you have a starting point. You need some sort of initialization to select which person you want to track. So in the earlier algorithms, uh, there was they were actually limited to single point tracking where you can only track one person at a time. And what you still need is like you want some sort of initialization that this is the person I want to track. So people actually either use points, like do a point as an input where you put a point at the center, or you draw a bounding box around the person to identify that this person is what we will be tracking into. And then iteratively at each frame you compute these gradients and you see that like in which direction this person is moving and you track the whole thing, right? But those all earlier algorithms were only limited to the this thing, right? Single person, like they were not multi object tracking. So those things actually comes like in a later stage where you can actually track multiple persons, right? And nowadays everything is multi object tracking, right? Just see what is the output of this, right? If you see this red dot, right, this is basically essentially tracking this person, and this is the basically tail, you call it the trajectory of that person, how it's moving. So I mean pretty decent, right? So it was almost able to track it to to the other extent, right? mm, no, no, I have to actually select it. I have to select a bonding box. So uh, let us try with this person. So you can see that like yes, yes, you have. This is CV2 functions, right? You can actually get coordinates of this bonding box. Yeah, yeah. So I mean, I'll share the code actually anyway. So I mean, you should play and see in what cases it basically fails. So I don't think so. I mean, I have not seen the assignment, but um, I have not seen the assignment, so I am not very sure. But it is unlikely, unlikely. Yeah, but I mean, it is useful. Like, when I moved to any like industry, so any object detection problem is basically followed by a tracking problem in most of the cases, because if you're actually looking into the real world cases, suppose you want to basically count number of people entering the shop, right? You cannot only use the object detection in that case, right? Because you need to track that person like till it enters. So you need some sort of a trajectory. You create a line, and if that person create like crosses that line, and then you say that like that person has entered the shop, right? So and you'd want a unique count as well, so you cannot uh, or do a detection, right? Always, so you detect once and keep on tracking till that person enters the shop. So now basically you, this is actually the more efficient way of doing a detection. So you don't have to do a detection at every frame. You do it at the initial and just track it, or maybe do it after few frames. Let us see how this goes. Just one more thing, I just want to check how does it do in the occlusion. So let us see. Just try to track this little girl. So actually, I think it has moved the tracker to its mother. Right, it has missed the tracker. These are the actually challenges in the tracking space. Any other person you wish you want to track and see their trajectory? Yeah, yeah, but yeah, yeah. See, tracker has moved, right? It's a very good example actually. It is, as you rerun it. In this case, it didn't actually. I think maybe the way the bounding box is initialized. I mean, not the center actually. It doesn't. I mean, I'm actually showing you the center to represent an object, but the features are from different space. Maybe let us see if she actually. But you understand the failure cases, right? And in case of like the partial occlusion or full occlusion, you kind of miss the tracker. So that is the issue with these kind of approaches, right? So uh, let us see if I can actually show you. Uh, was it? So you can see the screen, right? Google, Google Notebook, right? Okay. So before going into, just check this Ultra Analytics YOLO. I mean, actually, they are doing a very good job, right? They have quite a variety of quick start models. So earlier, what used to happen is like you need to create different modules for different kind of objects, like task, right? For detection, segmentation, classification, pose estimation is one of them. Even tracking is one of them. So uh, it was pretty difficult, and it was like completely different job altogether. But like these guys have actually combined everything into one repo. This is Ultra Analytics, and they are the like creators of YOLO 11. So YOLO has been one of the uh, what do you say, industry favorite because it's fast, very optimized, and it runs with the minimum amount of compute. So people have actually used that, and in the same direction they have also created multiple versions. YOLO v5 was there, then 8 xx was there, I guess, then 11 is there. So I mean, if you are actually using some sort of you want to solve this object detection problem, just I think I would recommend just start with this repo. And if your object is already present in like MS Coco, which has lot of objects like person detection, you don't need to train it again, right? It should be straightforward. You can actually do the inference directly. um, and if you have basically working on something which is slightly different from which is being present, so maybe some sort of a medical application, maybe satellite application, then you might need to fine tune it. So I mean, the objects like traffic cones, person, these kind of things are already present, and you should be able to like use it in with the very minimal code, right? It's some sort of a keras for object detection. So highly recommend it if you are actually building something on it. uh, I mean, they have given tutorials as well. Just see if it is useful for you. Even the segmentation also they have done quite a work, like. So in tracking also, multi-object tracking, they have a very decent tutorial and kind of APIs, right? Earlier you used to write this APIs on your own. Yeah, let's see. I mean, what libraries you guys use? Any? I mean, are you building anything? Are you working on any project? I mean, uh, okay. Sorry. But you can actually train it on this Kaggle and this collab also. So I mean, if it is too much compute, I think, yeah, sure. But like, if some sort of model you should be able to create using these things. So I think it is required to install it. I'll just wait for it to install. Okay, I think it is installed. Uh, yep. No. So, so I think CV2 is one of the libraries where you should be able to do multiple things. So the CV2.video capture actually is for loading videos, and if you just like, it will not work in this case, but like if you actually make it 0, it will actually access your front camera and like capture your video only, right? uh, and Yeah, so what we are doing is like we are loading a video. It is the same video which we have seen, right? We these are the few of the frames, and just ensure that like video loading is in a proper way, right? And it depends on what kind of tracking you are doing. If you are actually doing some sort of a region, you can actually define a region in the image where you will need to do the tracking. You can actually use the whole image as the region. Let us see. So the track zone is one of the function calls it is doing. And YOLO 11N, N is basically stands for nano. So this it is the smallest model in that case. There are other models as well like SML. So it is processing each frame, and you should have a output video here. Hmm. So this white box is basically the region which we have used, right? And let us see how does it do in tracking. Pretty decent job, right? Occlusion is anyway difficult for any problem, man. 203, where is 203? 203, let us. 203, yes, I was looking at. Yeah. Right. Yeah, she lost the track, right? 203. The new ID has been assigned. If you actually see that these IDs are basically ensuring that the person is tracked properly or not. If your tracker is basically assigning a new ID, that means you have actually lost that person between the process. And I think 203 is something which has happened. I think, but at this point it is difficult, right? But earlier I think it was, it should have done better. So what they do is like they extract features from use this object detectors using this like to get the bonding boxes, and in between frames they track. So like after basically 5 frames or 10 frames they do the detection again, right? And between those frames you track, and like if there is occlusion at during that frame, during those frames some sort you lost, you will lose the tracker at that point, because like now when you detect it's completely new object, right? You do some sort of a matching with the previous things. YOLO is basically a deep learning algorithm. I mean, it's pretty good actually. So you see that like most of these YOLO was able to detect, and it is the smallest. Like let us. I have not tried this, but shall we try with a bigger YOLO? Let us see. YOLO M. I mean, if they teach it, I don't think they'll teach it. But like the properties for an, uh, I mean, like if you have written that you used YOLO, then people will definitely grill you on that. Like they'll ask like what is the architecture, why it's YOLO, and what kind of framework is YOLO, right? So I mean, anyway, it is like um, you should write only whatever you are confident in, right? But in general, like people will ask you about the whole concept of object detection, right? How does that work? And then some specific about architecture, because there are multiple architectures which are present. Right, if you see that like now we are actually detecting multiple persons. So in this group earlier there was only one person which was detected, this one. Now we are basically detecting multiple things. Frisbee also, false detections. 201. You saw it, right? This 201 tracking. Yeah, yeah. We missed this tracker earlier. Other thing also, it's detecting back like backpack. It is saying it's a frisbee. But yeah, this is basically the multi-object tracking. So there are multiple objects and you're tracking multiple, all of them at the same time. And this is only possible because of this object detection framework, where you can actually get output for each object at a time, right? After few frames you're getting the output response and you're updating your tracker, right? So that like it doesn't deviate from the original trajectory. Yeah, so this is the object tracking. I mean, there are many applications for this as well. So if you remember, in car tracking also, people actually in the there are cameras where you see like people have actually identified device modules for speed detection, right? Maybe a number plate detection also, right? So what will happen is like there are cameras on the road and you have a vehicle which is going, right? But there can be multiple vehicles, so you don't want to do the detection at each stage. So what you do is like you detection at the first frame where the object enters the frame, right? Once you have seen that this is the object, you like track the object till it reaches a point where the number plate is actually visible, right? And then you basically do the like another, you call another module which basically say take a snapshot of like number plate and convert it into the OCR, right? So I mean, tracking is basically very like efficient way of doing things, right? If you look, like there was one problem which we were working on where you need to actually do some facial recognition in crowded space. So you cannot do the detection at each step, because then you have to do the matching, like suppose there are 100 target objects you have, target people you have, and you're finding out whether these people are present in the crowd or not, right? So at if you don't do the tracking, what will you do is like you do a detection, you get the bounding box around the image, your face, and you do the match, you match that, uh, match the features of that face with the your stored faces, right? And you do it at every frame, so there are 25 frame per second, right? In per second, right? 25 fps, I guess. Right, so 25 frame per second you get, and doing detection at such a large, uh, at such a high speed, and like so many, it requires basically a good amount of compute. So what people have actually figured out, if suppose this is the person with whom, like for whom I want to do the facial recognition, once this person enters the frame, what I'll do is like I'll keep on tracking it. Once it is closer to me, or maybe you define a region, I'll do the facial detection in only in this region. Once this person is in this region, I'll call my model to do the face detection, and then just match the face. So I'll be only doing it once or maybe twice, like if there is a loss of tracker, and then again I detect there is a person in this region, and then I call the my facial detection model, right? So we are basically saving a lot of compute in this case. So it is actually helpful in many ways, object detection and tracking. People generally use these days with object detection. So that initialization which we did for Lucas Candy, right? We did manually. Now people have actually moved to automatic initialization, where these object detector will initialize these bounding boxes, and the tracker will basically track them. And you can actually call this object detector after a few frames, so that like you can course correct any tracker which might have lost its course. Make sense? Yeah. Yes, so I think so. I mean, there are like hundreds of classes which are there. So backpack, it will do. It will, if there was an animal in here, it would have detected multiple animals: cat, dogs, tigers, elephants, giraffes, those kind of animals. It might have detected. There was a computer, chair, mug, cup, those kind of objects. So there are multiple classes uh, which can be detected using this object detector. So if you are interested in the person, just filter out the classes which has a person as a label, class label. Yeah, so it is also detecting these circles as the frisbee. Yes, yes, that's what they do. You can actually do it for each frame, but people generally skip few frames, right? Because there is yeah, so that's where the tracking actually helps, right? Because between two frames there should not be very much difference, right? Like just see this thing, right? Like there is not much difference between, like even if I'm pressing very quickly, but it is basically I'm passing multiple frames, so it is not much difference. So the object is still at the same place, so you don't need to do the detection at each step. So you can actually skip few frames and do the detection, so that you can actually course correct the tracker. Yeah, but if you skip many frames, in that case you'll the tracker might basically lose, and then you, when you detect again, you'll see that like it assigns a different person ID. Yes, so I mean, using the frame one features, it has identified some key features, and you can actually see in what direction these are moving. So that like now you see that like if you compare between these two frames, you see that like the feature have moved into this direction. Mm-hmm. Mm-hmm. It is a multi-class classification, yes. There are multiple instances of the same class, yes, definitely. Hmm. Softmax is used to identify. Yes. Yes, yes, go ahead. Mm-hmm. Hmm. So, I mean, there was something called as the like if you look at the literature of object detectors, those are primarily two categories. One was the single stage detector, and or the other one is the two stage detector. What you have explained in the like first one like is basically two stage detector where you identify features and you pass those. So there are two type of object detectors, right? One was single stage detector. The other one is the two stage detector. Two stage detector, in what happens is like in the stage one you identify certain regions or certain features, right? And you give those features to a classifier to say whether there is a person present in that region or not, or matlab, or like maybe you say that like whether not exactly, but closer. Yeah. So this is a very easy explanation. Yeah. So you can understand, maybe, yeah, like that's what happening. But in true sense, you identify region proposals. They don't call it bonding box. They call it region proposals, and region proposals will not be well like very squarish. They can actually have any arbitrary shape, like maybe in a form of a polygon also. But what you do is like you pass it to a SVM classifier, which basically say that like whether there's an object present in there or not. So this is the two stage part. What happen in single stage is the output layer looks like you have uh, basically for every object you have five properties are there, five like six properties are there. First one is basically the class of that object there, because there are multiple classes. Second is the confidence. YOLO basically predicts the confidence as well. Like then there are four coordinates of the bounding boxes: x, y, width, height, right? And because there are multiple type of object detectors, people use different type of format for bounding box. Maybe some are center coordinates, some use like top left and top right coordinates, some use like only top left coordinate and width and height. So it's basically a regression problem at that point, because you are identifying the like exact coordinates in the pixel space. So these six uh, are predicted for each instance. You understood, right? For each instance, right? So if there are like 25 objects, there can be, suppose there can be 25 objects uh, in a frame, like, so that like now you have 25 into 6 should be the dimension of your output layer. You define what is the maximum number of objects which can be present in the output layer. Suppose, right? So you suppose you say that there can be 100 instances, 100 object which can be present, and you each instance have six attributes, like which is the class, confidence, bounding box, right? So 100 into 6 will be the dimension of your output layer. And yes, yes, YOLO is a single stage classifier. Yeah. And yeah, I think nowadays it's 300, I guess. Yeah, I've not checked. I've not checked. I know for another detection model which I am using for my project, they use 300 proposals. Yeah, they 300 objects they can detect. But you can actually increase it, right? It's a matter of how much computation you need. But like it like I don't see there are many data sets which actually require a frame to have a 300 objects present. Yes, 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 yeah. So what I have not seen, like we I work on cell detection problem, and we have close to 100 to 150 180 objects per frame per image, right? And that is, I guess, maximum I have seen. There are hardly one or two data set basically. Maybe the crowd counting data set has more object, 200 250, but like I think 300 also is kind of a upper limit for this problem. Yes, yes, yeah. So I mean there is one. Yeah. Yes, so there's something called as the bipartite graph matching. So some sort of a cost function is there which you want to minimize, so that like you can actually do the matching. So using that, you find identify which is the best match for that prediction, and you match it with that bounding box, compute the IOU, basically intersection over union, and use it as a loss. So there are three losses, I guess. One is the objectness loss, which is basically determines whether there is an object or not object. So, right. Second one is basically what is the class. Third one is uh, basically your bounding box regression problem. So, and for bounding box, people use IOU as a metric, intersection over union. So what they do is like they find the intersection of two bounding boxes and divide by the union of two bounding boxes, and the range is between 0 to 1. right? If there is a intersection is greater than zero point 0.5, they say these are the overlapping bounding boxes, and they sometimes they say that like these it matches basically, right? And person where is there is person 4, yeah, 16 and 4, right? No, a person 4, yeah, okay. No, but overlapping I'm talking in term of training. So suppose what it does is like suppose this is the person force ground truth bonding box, and you have a prediction something like this, right? Right, or maybe just half the prediction only. You misses the head part and just do a bonding box from the shoulder. In that case, if the intersection over union is greater than zero point 0.5, you assign that yes, it was the same person, but the bonding box dimension should be better, right? Maybe you just you detect bonding box from head to knees only, right? Then you missing out the leg part. So in that case you say that like okay, this is essentially the same object. I have done a decent job in detection, but my dimension of the bonding box should be improved. So now, but like now you have this, you use this as a loss, 1 minus IUU as a loss, and you back propagate it to improve the prediction like of the bonding boxes. Yes. Yeah, and the softmax you're talking about is basically the classification loss. So you have for each instance, right? Each instance can be classified into 100 categories, and you pick the one which has the highest confidence, that is person, right? So this classification or the softmax is for each instance, not for whole frame. So each instance has a softmax on, like, you for each instance you do a softmax and find out that which is the most probable category of the class. Makes sense? I'm thinking. Hello, am I audible? Okay, okay. So I mean, it is clear, right? Like we should move ahead. Hello. Can you see my screen now? Right? Unit like with convolution neural network for biomedical segmentation. So this is basically the segmentation problem. So I mean there are differences in the detection and the segmentation work, right? So let me just give you detection. There is one nice article. Right, so this is a very good. Let me just share this tab. I hope you can see this Medium article. So this is very good example of object image segmentation, right? So in object detection, you have a bounding box corresponding to each object, right? So there are two dogs and one cat, and you have three bounding boxes. In segmentation, instead of bounding box, you have a pixel level annotation for each object. So you have the exact boundary of like um, your object. So in the even the segmentation problem, you have different type of segmentation. So there's something called as a semantic segmentation, where both of them should be segmented into the same category. So because both of them were dogs, right? So these two should have the same color, maybe red, and then this is a different category, and this is a cat, right? So then it might have maybe blue color. But there is another way of looking into it. It's called as a instance segmentation, where you segment each instance with a different uh, like maybe not a class, but like you define it as a like each instance as a unique id. So now that's why there are three colors: red, green, and blue, right? And what is the objective here is you want to assign a class to each pixel in this image. So where there is neither red, green, or blue, it is assigned as the background class. Right. Let us see if there is any other better image. Yep. Right. So this is the whole problem. Just if you look into it, is basically. Let me just share this one. Yeah. So there are four type of problems. So one is that you have an image, and what you do is like you identify what are the different instances which are present. So there are three sheep which are present, and there's one dog which is present. So what your model says, like it gives you probability for each. It gives you probability for whole image, right? That what are the objects which are present. So it has 0.6 probability that there are sheep in this image, but it will not tell you that how many sheep are present. There is 0.3 probability there is a dog which is present. So but also it will not tell you the localized location where the dog is present, or how many count of number of dogs which are present. Then there's something called as a semantic segmentation problem, where you assign a single class to one type of object. Like suppose sheep has been assigned a blue color, right? This is all one class, and the dog has been assigned a different color, so this is another class, right? So this is the semantic. So semantics of all the three object is same, so it doesn't differ whether it's a labrador or a golden retriever. They just play at a higher level or an abstract level, that both of the categories are a dog, and both should be characterized as a dog, and even the sheep also. Then there is something called as object detection, which we have seen for tracking purpose. And in you what you do is like you assign different like instances, or maybe in some cases you do like different class for each object, where you represent each object by a bounding box, right? Where the dog is represented by the bounding box, sheep is represented by the another bounding box. There is something called as the instance segmentation, where each pixel is assigned to a class, and different instances also are assigned given a unique id. So this might be one unique id 1, this might have the pixel, all these this sheep might have the pixel values of 2, this might have the pixel values of 3, and this might have the pixel values of 4. So apart from different classes, you assign different instances also. So this is broadly the case. So, like the most of the research has been happening in this four spaces, whether it's image recognition, object detection, instance segmentation, semantic segmentation. And like in more or less people have kind of beaten the initial benchmarks, and they are actually kind of, so these all the cases are like very good in general natural setting. So if you look at any, if you take any, what do you say, object detector and just run it on natural images, you capture it from the phone, you should be able to do some decent job, right? But for very specific problems you might need to collect the data and train it again. So what we will be looking into it, we will be looking into the semantic segmentation. I'll just take a quick pass over the paper which we were discussing, and it basically it was one of the pioneer papers in the segmentation space, and YOLO was one of the pioneer paper in object detection space. Make sense, or like any doubt in this case? Okay. Okay. uh there is, I think these topics are actually easier than your geometry. I think the geometry part is the most difficult part of the whole computer vision. Even the 3D points is somewhat complex because everything comes from there. Yes, yes, definitely. So the traditional computer vision is slightly more complex because they it's been always been the feature driven. Like once there are 2012, I guess, they released ImageNet, which was one of the biggest data sets for images. And after that, like I think in 2015, from 2015 people have actually started exploiting these bigger data set and moving towards I think these deep learning based architectures. And now I think in uh, because sometimes those features actually like because they form the base, so everything has been. No, like I mean we have seen that like these are the CNN based architectures, and what people used to do is like they used to learn these design these features for a particular application. But now we have so much data that like your model converge to that filter if you want to solve that task, right? So those filters actually form the base of these deep learning models, and the properties there are still helpful. um, in cases where your model, your data is very limited and you want to push it. So suppose there was one problem where we were actually looking at some images, but there was the contrast between the foreground and background was not that great. So what you do is like you force your model to focus on the edges. If you do edges well, you should be able to do the rest of the things better. So I mean, you what we have done is like we have also fed, explicitly fed the Sobel operate like output of that Sobel filter uh, by saying that like your use this as additional information if you're not able to learn it. And we saw that like there was an improvement, and maybe, yeah, we were actually training some sort of auto encoder in that one, and the reconstruction and the shape, even the edges were not that sharp. So using that Sobel filters actually helped. So yeah, I mean you can actually bring out these traditional ways into the new deep learning architecture whenever you're stuck. So it's good to know, have the, like, good to have these weapons, or like, so that like you know uh, where to use them. So yeah, yeah. So this is basically the unit architecture, where what you're doing is like you have passing input. Suppose your input is basically 572 cross 572, and you are basically doing that. You are, this is your first convolution layer, then second convolution layer, and then like you are kind of increasing the number of filters. So in first case, the number of channels are 64. In second, after second, in the second layer, you have the number of channels 64. So you are increasing the number of channels by introducing, learning more and more filters. But what they have seen, they have what they have done is like they have created it in a U-shaped architecture, where what you're doing, what they are saying is like, uh, like uh, you are learning local and global concepts. So uh, these at when you are at this place, you will have a very large depth, that is the number of channels, and each filter will have a receptive field of maybe a bigger region, right? So now this point is basically learning the global features, and these initial layers are basically learning the local features, and you are basically learning at various hierarchy. And they say that like the intuition is like when you basically want to see anything, what you do is like you see, if you see at the various magnification, you get a better sense that like how that object is at various magnification, and you learn a better representation of that object. So like you see at a very high level, then you zoom in, and then you zoom in, and at each step, each magnification, you are basically like required to learn these features, right? And because you are basically forced to learn this feature, and your next step is basically dependent on your previous step, right? So you understand how this object looks at various magnification, and that actually helps in overall understanding of the object. So it basically gave one of the like best results at that point of time, and it was super easy to train, right? And this became like really popular. So what if you have an input image, right, and you're basically producing a segmentation map. So when you're doing a segmentation map, you are basically predicting two channels. First one is maybe your background, and second one is your foreground channel. You can actually do the both of them into the same channel, right? Like if you just predict two like pixels, so either you predict black, or you predict one, zero or one. If you predict in the single channel, you should be able to do the same thing of background and foreground separation into the single channel only. So what they are doing is, for each pixel, they are predicting the probability that pixel is basically foreground or a background. So let me just see if there's a, yeah. Right, so just assume that there is no dog here, there is only goats here, right? So for each pixel, like if there is a grass, the probability of, what do you say, the background channel will be higher, so zero point 0.9 at this point, right? If I am at this point, my foreground probability will be zero point 0.9, and my background probability will be zero point 0.1, something like that. So these are two channels, and each represent background and the foreground, and whenever I take the max at each position, right? So at 0 0, what is the max? So if the max is coming from a background, I assign it as the zero level, so it basically gives me a binary mask. So between, like, it which has value 0 or 1, either 0 or 1. And now I should be able to see that like how does the boundary of an object should look like. But like and but like how do you train it? I mean, that should be the case, right? Should be the question. How do you train it actually? But you understood, right? What is the problem and what are we trying to predict? So what they do is like they uh, do a cross entropy kind of prediction, in right. So if there are only two classes, you do a binary cross entropy at each pixel. So where like p is basically probability for each x is basically for an image, it denotes the pixel position, right? So for each pixel you say that what is the probability of being at that class. So it can be, and you play between 0 and 1. If it's a background, you try to maximize the probability of 0, and if it's the like foreground, you actually try to maximize the probability of 1, right? But I think this is the log likelihood, so you actually maximize uh, the 1 only, so the other one even like anyway goes to 0. And they have found out that there were cases where you do actually augmentation, data augmentation, that helps. And I guess this is the results, right? This, even if these images do not have a very defined refined boundary, you should be able to get a good decent predictions, right? So but after this paper, the field actually exploded, and people started using different kind of architectures for different kind of problems. And even what they have done is like they have used different, like maybe different encoders as well, so stronger encoder to extract out features. Now what you have seen is like we are learning all the features, but you don't need to learn all the features. You can actually use some sort of a ResNet architectures where you can actually extract out features from ResNet and then use this decoder like U shape architecture to just predict the like what do you say, the segmentation map. So yeah, I mean the progress actually become very, what do you say, fast after this this architecture. And I think in next session what we can do is like I'll just show you maybe I'll see if I can train something and just show you the results using this from training from scratch, and maybe using ResNet feature encoder, like what is the difference, and maybe the convergence and the accuracy. And how do people actually evaluate it? You have thought about it? Like, what's your thought on that? Like, suppose you have a ground truth segmentation mask. Between have pixel value 0 and 1. You have predictions which you can convert into 0 and 1, and then how do you basically evaluate these two segmentation masks? Any thought? Okay, I think we will see them in the next session. But you actually okay. So and I can repeat it. So what I'm asking is how do you evaluate the segmentation masks generated by the model? So you have one segmentation mask which is generated by the model, you which is have probabilities, right, for foreground or the background. What you can do is like you can actually do take a max and use convert it into 0 and 1. So any pixel, each pixel will have either value 0 or 1. Okay. And you have the ground truth mask which is basically in a format, binary format, with value 0 or 1. So what I'm asking is how do you evaluate the quality of the segmentation? How good was your predictions? Okay, I think we should be able to see it in the next session, but like I'll just give you the hint. So, I mean, you can actually see how many pixels you have correctly labeled, right? So, what you can do is you just uh, identify how many pixels were one in your ground truth and identify how many pixels were are one in your predictions, and just do a accuracy match, do compute the accuracy. So suppose there were like 100 pixels and now you're only predicting 86, then you're just 86% accurate, right? So this is one metric. So the another one is basically the dice or IUU also. So what you do is like for every predicted pixel, if it matches with the ground truth pixel, then there, it's called the match, right? And but if there are over their model has predicted more in the ground truth, but their model has predicted more but there is nothing in the ground truth, then your model should be penalized. So the IOU should be like close to zero in that case, right? There is no intersection between the ground truth and the predictions, right? So IOU, there is something called the dice mask is pixel wise. Yes, you actually use mask as a pixel wise. So each pixel has a mask. So it is essentially an image, but at each point, at each pixel of the image, it is giving you the probability of being at the foreground or a background. Like let us assume that there are only two classes, like either it's a background or a foreground. But even if it's a multi-class classification, you'll have the softmax, right? Where you have the maximum, like you take the maximum. Eventually boils down to a single value at each pixel. So you're at each pixel you'll have only one value. You'll have class value for each pixel. And that's what. Mhm. You can have multiple. You pick the maximum value actually. You cannot have you. Mhm. Yes. Not regression. It's a classification problem basically. Right, but you want to do is like you want to still want to maximize the probability, right? So you are basically maximizing the softmax for that class. Yes. Yeah. Yep. Yes. Yeah. Yeah. That's what you do. Yeah. That's what we do. So there are two main losses, right? Accuracy. Uh, Losses is basically cross entropy and dice. People generally use dice also along with cross entropy, but initially they started with the cross entropy only. In term of evaluation metric, there are multiple evaluation metric. The most popular was people actually check the accuracy. People check for IOU or dice score for them. But like now the literature has evolved, research has evolved in this direction, and there are multiple loss function. MIOU is something which basically I think we should be able to see them in the next session. Yeah. So, okay, I think I'm almost done. Uh, if you have any doubt, just post it in the this discussion channel. We, if I get any, Any questions? I have not seen the next assignment, but if I find out there's anything which is essential and not there in the lectures, I'll definitely take it. I'll just see in the next session, right? When it is due, your assignment? Assignment 5, right? It is on 4th. Mm, we have seen most of them. Uh, just see if you're able to see go through it. But you might have to. Have you gone through the week 10, week 11 lectures? No. I would say, I would say just go through them quickly and then go back to that particular problem, right? So, um, like just yeah, I think that is the case, right? Like you just see the problem and then go back to the like lectures. I think most of them are theoretical. I mean, you should be able to do it. I mean, there are only two of them are like numerical questions. Just see, just see if anyway I'm not able to. Well, I should not be taking. I should not be discussing these questions. Uh, but if you have any doubt about any topic, I think just put it in the chat. I should be able to answer it. I'll do my best. Yep. And this is week 11, right? There is one more week. Week 12 will have assignment, I guess. One more assignment. I guess at least one should be there. Let me just see. Yeah, I think it should have one more assignment, I think. Assignment and one quiz. Is it? I mean, I don't know, right? I'm not keeping a track. Yeah, but I think next week there is one, definitely a quiz, but I don't, maybe assignment as well. Mm, yeah, but how are you feeling overall? Like, what is the state at this point? Like, CNN was. Yeah, understood. Hmm. I think week 8 and week 9 is somewhat like difficult. I think I would suggest let's take a like just have a look again once. But like this time, hmm, okay. So yeah, I have not gone through week 10 till now, but uh, yeah, but yeah. I mean, if you have any questions, like we can take it up. But I mean, just assignment 3. Yes. But I think in the yeah, yeah, I understand. But like I think they eventually, I wish everything should come to another like better sense, right? Like once you actually have gone through all the lectures and what we should do, like how many? This is week 10, right? I have two more lectures, right? Math, I think you cannot. Hmm. Just see online if you can actually find it, so find out some of the good. So just check for, like there are, just check for Stanford have this machine, this computer vision courses. Check for their midterm and term exams and see you can actually get good questions there. You can practice. I mean those are very good, and they should you should be able to get the solutions also. So if you practice those will actually give you a very good sense of what is going to happen in the exams. Yeah, so those are actually very helpful. When I prepared for my exams, I actually go and do that. So I mean pretty very helpful, even if those same question will not come to the exam, but like they actually clears the concept in a better way. I'll see if I can take up. I have been using, I'm been discussing those questions like whenever we are actually going in our discussion. So I'm also referring to them whenever I'm discussing. So if you want, you can actually see, you can get, if you can get more, something more out of them. But pretty much useful, very useful. So I have two sessions. One, let me see if, I don't know, right? Like, I mean, uh, maybe uh, this week 10 I'll spend one lecture on there. Or if you want to know more about deep or like newer things, I mean it's up to you actually. I mean there are not many people in the session, so pretty much like uh, moldable if based on your uh, weaknesses. You can actually have a say here. I mean so I'm fine, like if you want we can actually go much deeper into more recent stuff, but we'll spend some time, some spend. Yeah, I think more industry, not I'll not say industry, but in a more recent way, what the research has been. So I think that would be beneficial for you in the longer run. Okay, then I think we should close it here. Let's meet next week. Segmentation we will take and see if we can talk about detection. I'll just show you a few of the examples. Maybe a code for detection architecture. Let me see. Yeah, but it will be something like more recent. Yeah. Okay then. Thanks, man. Thanks. Okay. Bye bye.